Hello everyone! I recently wrote a little Rubik's Cube solver capable of completing the cube in about 8 seconds and using 40 moves on average, though it occasionally gets stuck. So today I want to experiment some more, hopefully making it perfectly consistent and much more efficient. I'll be relying mainly on the suggestions you all left on the last video, so they better be good. One idea was using CFOP to solve the cube and seeing how that compares. This is a 4-step approach popular among human solvers for anyone unaware, which begins by first constructing a cross. As a quick example, if we want to make a white cross, let's say, we can first locate the white center, and I see this white-blue edge is filled in already, so if we grab the green one up here, we can put that in opposite blue where it belongs. I'll also slide this red edge in, and then only orange remains, which can be slotted in over here to complete the cross. Notice also how it lines up with the surrounding centers, since I was careful to put the colors in their proper places. Okay, so the cubelets we care about for this case are the edges in the first layer, which we labeled 0 through 3 in our numbering scheme. Obviously they'll be scrambled up to start with, but we can just look at which edges are in those positions and award points for any correct ones. So I've implemented that in the code with this little loop over the first 4 edges in the cube state, testing if each one is the value we expect, and increasing the score if so. I'm giving 100 points for each one, by the way, because we also want to incentivize shorter solutions by deducting points for each move it uses, but of course making progress is most important. I'm using the same search code from last time with this, which starts out looking 6 moves ahead, and if it can't find a way to make progress, then it increases that to 7, and finally 8 before throwing in the towel. Going deeper would start taking minutes and hours, which is no fun to wait around for. Alright, let's shuffle up the cube quickly and see how it goes. Okay, that looks like a cross to me, so step 1 of CFOP is in the bag. Next up we have the first 2 layers, and that means just filling in the correct corner and edge cubelet over here, and all the way around the cross. So for example, we can see this white-blue-red corner up top and the blue-red edge that belongs next to it, so we can pair them together like this, and slot them in where they belong. It takes a bit of practice to get the hang of this, but it's a pleasantly intuitive process once you do. So here I've just slotted in blue and orange, then I'll do green and orange, and finally red and green to finish the first 2 layers. If this is something you'd like to learn, by the way, there's a bunch of great cubing channels out there. Like, I've learned a lot from watching JPEM in particular. But to pass the knowledge on to our program, we can simply create a new score value for this stage, which I've made lower than the cross so it doesn't break up any of its progress there. Then that new score is just awarded for any edge correctly placed in the second layer, or corner correctly placed in the first. Alright, I've got a scrambled cube at the ready, so let's run the solver. And okay, that is looking good. I'd like to see it try another one, but let's view it with the cross on the bottom this time, since that's how you'd typically see it when solving by hand. Let's also engage our X-ray vision here, so we can see how it all comes together. Or not, as the case may be. We've ended up with this second layer edge solved, but the corner beneath it is twisted, and the same thing has actually happened on the other end as well here. Having a closer look at this case, it seems it would take 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 moves to resolve, but our search only goes to depth 8, which explains it getting stuck. What it should be able to see though is if it just focused on fixing the corner, that could be done in 1, 2, 3, 4, 5, 6, 7 moves instead. I guess it has no incentive to do so though, since the score for a correct corner or a correct edge is equivalent, and we've just traded one for the other here. So I've patched that quickly, simply by separating the score for this stage into a higher value for corners and a lower value for edges, and using those over here. Alright, let's run the same scramble it was getting stuck on before, to see if it's any smarter now. And it looks like that has done the trick. Running it some more though, it soon got stuck on essentially the reverse of what we just fixed, where the corner is correct but the edge above is flipped around. So I've gone and added an explicit penalty for this edge case in the code, just detecting correct location but wrong orientation in the second layer. So it knows to move it out of the second layer, at which point we'll be able to see far enough to insert it back correctly. Or more often, I guess, it will avoid even landing up in that situation in the first place now. Alright, I've just finished running this 1,000 times, and it seems to be perfectly consistent now, averaging around 28 moves for these first two stages. For human speedcubers, 35 to 40 is typical, I believe, though they're concerned more about what the fingers can do fast than about saving a handful of moves, of course. Anyway, that brings us to stage number 3, the orientation of the last layer. So that means twisting all of these cubelets here so that the yellow side is facing up. The way I've learned to do this involves one sequence of moves to orient the edges, and then depending how the corners land up, I have another sequence memorized to correct those. I think prioritizing the edges could be a good idea for our program as well. That way it has a sort of halfway goal to work towards in case it can't see the entire solution from the start. Another approach could be to simply plug in the 57 different cases that people have figured out for this stage, but I think it's more fun if the program has to find the way itself. Things were threatening to get messy in the code though, so I've separated it out into one loop for the corners and one for the edges. Looking at edges first, I've refactored a little, but all that's new is this line here, rewarding edges being oriented in the last layer. And then same story for corners, though those get a lower score as we just discussed. Alright, let's test this out, starting from a position with the first two layers already solved, and see how it goes. Okay, it formed a cross and then got stuck. I guess we'll need to give it a little extra guidance, so I know there's a short sequence of moves that keeps the cross intact, but cycles through different configurations of the corners. Applied in the right spot, that can get us straight to having just one corner oriented correctly, and applied again from there, it can then orient the rest. So having only one corner oriented is actually better than having two. With that in mind, I've tweaked the evaluation slightly so that it counts up the number of oriented corners, and only awards points when either just one or all four of them are correct. Let's put it to the test with the same starting position that stumped it before. And it seems to have kind of just bypassed the exact point it got stuck earlier, so I'm going to load in that tricky configuration to force it to go from there. And it does indeed do the maneuver we looked at, first going to the single oriented corner case, and then from there orienting the rest, though it found a different set of moves for that last step. Okay, with that, we have arrived at the final stop of CFOP, the permutation of the last layer. And that means moving these cubelets into the correct positions now, without messing up the orientations, of course. I've learnt again a simple two-step method here that first corrects the corners, and then corrects the edges. But I believe we're close enough at this stage to finally just brute force the rest of the way in our program, because everything is oriented, meaning we can cut out some of the moves like we did last time to speed up the search, which makes deeper searches viable, of course. And we can also use the backward search lookup technique from last time as well. Alright, I've got a shuffled up cube here, and let's see now if our CFOP solver can solve it. So it's doing the cross and simultaneously setting up for the first two layers, which it goes about in a kind of confusing way, to my eyes at least. But now it's on to the orientation of the last layer, and finally the permutation. Okay, that solve was a success at least, but let me run it 1,000 times as usual to test the consistency. And the results are in. We have achieved a 100% success rate, which is very nice, along with an average computation time of 6 seconds and move count of 56. Here's what the distribution of move counts looks like, by the way. So we can see in rare cases it found solutions in the mid-30s, and in other rare cases it took as many as 80 moves to solve, but mostly somewhere in the upper 50s. Then I've also made a little overview here, where we can see the shortest, longest, and average solve values, both for move count and computation time. Comparing this to the solver from last time, that one was obviously less reliable, but a fair bit more efficient move-wise, averaging around 40 instead. So it's been a lot of fun giving this CFOP style a go, but I want to embark on a mission now to make a much more optimized solver. And the term that keeps cropping up is Domino Reduction. I was sort of squinting at this concept last time, and several commenters were kind enough to put it into words that I could understand. It actually builds nicely on where we left off before, so as a quick refresher, let's say we want to take an edge, such as this white and green one over here, and reorient it so that white is facing upwards instead. For that, we could twist the front face and then the right face, and that's mission accomplished. But say we now choose a pair of faces, either left and right or front and back, to forbid from turning. I'll go with front and back like we did last time. This now makes it impossible to return the edge to how it was at the start. Like, if I just tried to do it anyway, well, I'd want to put it here maybe and then twist this up, but it's not allowed. So all we can do is move the edge around. We can no longer affect its orientation. What we did with this idea is first make sure that all edges are correctly oriented using this evaluation function, and after that we cut front and back turns out of the move list to drastically reduce the remaining search space. So same idea that we borrowed just now for the last layer of the CFOP solver. But if that was so successful, why stop there? We should cut out left and right turns too. Well, of course, that would leave us only able to twist the top and bottom, meaning the cube would have to essentially be solved already. However, we could loosen the constraints a little, like rather than forbidding front and back and left and right entirely, we could still allow half turns of those faces. That way, we're able to still move pieces between the top and bottom layers at least. We would have to ensure that all the corners are also correctly oriented first, which is to say white or yellow on either the top or bottom side. Like if this corner here had white facing forwards instead, obviously a half turn is never going to be able to fix that. Another thing the half turns can't change is which edges are in this middle layer here, so we need to have the right ones in there already. They don't have to be in the correct locations within that layer though, since for instance say we need to swap this green and orange edge with this blue and red one. We could do a half turn on the right, then on the back, and on the right again, and that is indeed swap the two of them. Alright, so I've tweaked the evaluation function now to try and achieve those additional requirements. It still rewards orienting edges, but now also placing them in the middle layer if they're supposed to be there, and it rewards orienting the corners of course. Then apart from returning a score, it also checks if all the cubelets meet the requirements, so we have an easy way to tell if the domino state has actually been achieved. Domino, by the way, is the name for this 2x3x3 variant of the puzzle, in which the top and bottom faces can be rotated in quarter turns as usual, but all the other sides can only go around in half turns. So essentially we're aiming to reduce the full puzzle into this simplified form, with the distinction that we do still need to solve the edge locations in the middle layer. Anyway, let's try running this on a random scramble, and we want to see all white and yellow on the top and bottom, which would mean the corners and edges there are correct. And that is looking good. And then for the middle layer edges, using the orientation rules we defined last time, green and blue need to be pointed forwards or backwards, which is the case here, so we have indeed achieved our domino. Now in the code I've listed out the move indices that we want to allow in this state, and filtered the full move list based on those. Then when a search is started, we can first evaluate whether the cube is in the domino state, and choose which set of moves to use and what depth to search to, based on that. When in the domino state, the search is also switched to using this evaluation instead, which is essentially the same we've used before, simply checking if the current cube state was encountered in the backward search, meaning we found the optimal path from this point, and if not, then falling back to a simple scoring scheme that tries to naively solve as many cubelets as it can. Alright, let's see how it goes. The score for the domino state is 2000, so we can see it approaching that rapidly, and it's immediately found a solution with the backward search from there. Okay, that's looking very promising, but I'm going to run some tests. We've ended up with a 95% success rate here, which is kinda bad, but I'm sure we can improve that with more depth, and the solutions it is finding are much better than before, with 26 moves being the average, and the longest one being only 33. Just for fun, here's the CFOP move count distribution again, and we can compare that with our new domino approach. Okay, so having improved the move count a lot, let's focus on bringing down the time bar next. One simple thing we could try is just replacing the fixed depth search with a loop that starts at depth 1 and keeps going deeper and deeper until either the limit is reached or the goal is found. And by goal I mean the domino in the first phase, or the true solution of course in the second phase. Even though we run many more searches this way, we can avoid progressing to the exponentially more expensive higher depths if a goal state is found early on. I left this running for a while to test, but when I came back I found it simply spinning its wheels. This bug had me baffled for a bit, browsing the search logs in bewilderment, but it turned out to be a very silly mistake as usual. Basically, after the domino is found, only a subset of the search threads are used, but I was still looking for the best evaluation across all of them, and that happened to be one of the old searches, since the fallback evaluation of the second stage wasn't giving a higher value than the first. So I fixed how the best search is selected, and I'll also add an offset to the evaluation here to ensure the second phase always scores higher than the first, so it doesn't suddenly think that it's failed to make progress. Okay, time to test again. And we can see from the results here that this iterative deepening approach has given us a decent little boost in performance, roughly halving the average time from around 13 seconds down to just 6. Now, my inclination from here is to dive deep into the weeds of optimizing the move-making code, but I know from spending half a chess episode on this sort of thing that searching faster doesn't actually get you all that far. The real trick is searching less. So we want to cut out useless sections of the search, and to do that I've gone into our domino evaluation here, and to start with tried just counting up the number of edges that are still incorrect. Now, a single move affects 4 edges at a time, so if we imagine there are 5 bad edges, for example, it would require at least 2 moves to fix all of them. Probably more, but we know for sure that it can't be solved any quicker than that. And so if we then see that there aren't enough moves left in this branch of the search for even that optimistic estimate, there's no point to continue looking. The actual pruning is performed in our recursive depth-first search function, so if the evaluator flags the branch as futile, we simply exit early over here. After running some tests with this, I was surprised to see the success rate go up to 98%, which I'm not entirely sure how to make sense of, but I'm not about to complain either. The move counts weren't meaningfully affected, but I'm happy to say our time bar is looking a lot tinier. What we've implemented now is known as Iterative Deepening A*, by the way, since it borrows from A* pathfinding, the idea of using a lower bound on the remaining distance to speed things up. Anyway, now that our search is so much faster for the first phase, we can try turning its maximum depth up a notch and see how it goes. Oh, I've run out of space on this page though, so I'll need to squish the UI down slightly. Alright, we can fit our latest test on the screen now, which excitingly has reached a 100% success rate. Of course, there could well be cases that it still fails to solve. This is only with 1,000 tests after all, but still it's good to see some green again. In terms of move count, the extra depth is letting it find slightly more efficient solutions, averaging 25 moves now, down from 26, though naturally the time bar has grown back a fair bit in return. I think our goal for the moment should be to just try and shrink it back down again, so we can increase the depth some more, and hopefully find even shorter solutions. Let's revisit the pruning then, and I want to replace the crude estimate we just made over here with an exact value, which should allow even more pruning to take place. So at startup, we can run another little search that begins from the solved state, and after each move simply takes the current edge data and clears out everything but the orientation information. With that, we can then create a lookup table telling us how many moves are required to correct any of the possible configurations of edge orientations. Alright, running this now, we can see our table is being generated in 3 milliseconds and contains 2,048 unique entries. You might think there should be 4,096 entries, by the way, since that is 2 to the 12, where 12 is the number of edges, but in reality the orientation of the 12th edge is determined by the others. As a consequence, it is impossible to solve a cube where just one single edge has been flipped around. We can fix the edge, of course, but another one will have to have been flipped somewhere in the process. So the only way to resolve it is by plucking an edge out and putting it back how it belongs. Good thing I realized that immediately and totally did not waste an hour trying to debug code that was in fact working fine the first time. Anyway, I quickly did the same thing for the corners too, so literally just running the same search again, but with a flag to use the corner orientations as the keys instead. And here's some information about that table too. It's a tiny bit bigger since each corner has 3 possible orientations, but they can always be solved in 6 moves, compared to 7 for the edges. Okay, so now in the evaluation function, we can use these tables to look up exactly how many moves are needed to correct the current edge and corner orientations individually, though we don't know exactly how long solving both together will be. But it'll obviously take at least as many moves as the longest one by itself, so this gives a good lower bound for our pruning. Alright, I'll run some tests on this quickly. And that has given us another good boost in performance, going from 3 seconds per solve down to just a quarter second on average. I want to trade these gains right back for shorter solutions though, so I've quickly increased that domino search depth again, by 2 this time in fact, which we can see has indeed improved the solutions, the average move count going down to just 23, with nothing taking longer than 26 in the 1,000 random scrambles I tried. I want to see how much lower this will go if we increase the depth even more, but I hate waiting ages for the tests to run, so let's see if we can't slip another performance improvement in first. And there is one more thing we can use for pruning still, which is the locations of the edges that need to be put in the middle layer. So same way as the others, I've quickly generated that table as well, which is the smallest of the 3, always solvable in 5 moves or fewer. Unfortunately, this seems to only speed things up a tiny bit though, so perhaps we could combine it with the others into one giant table, meaning we then get exact move counts rather than a lower bound. But running the numbers on that, it would need about 2 GB of memory, which seems a bit on the heavy side. Okay, I had a quick look online, and apparently there's some clever symmetry stuff you can do to get that number way down and then compress it into about 30 megabytes, which is quite impressive. I don't have the stamina to study these symmetries now though, so I'll settle instead for simply combining each possible pair of tables. That way we can improve the lower bound with very little extra work. We basically just need to combine the keys together during the search. So here for instance I'm combining the edge and corner orientation keys, taking care to shift one over so that the bits don't overlap. Doing the same sort of thing with the others, here are the 3 combined tables we've ended up with, each individually solvable within 9 moves as it turns out. These took about a minute to generate, and actually went on a bit of a silly side quest optimizing that down to just a second or so, but I won't bore you with the details because I ended up storing the results in a file, so it was a slightly pointless exercise. Anyhow, I'll run the 1,000 tests again with our new tables, and it is really flying now, so I'm excited to see the statistics. And we can see here that the average time is all the way down to just 33 milliseconds. So let's get back to improving the move count now by increasing the depth again. I saw on that site that the first phase is completable within 12 moves, and the final phase within 18, so let's use those values for our new search depths, though we only need 10 for our final phase since the backward search covers the rest. This should guarantee that our solver always succeeds now, which also simplifies some things, like we no longer require a fallback evaluation if we know for sure that our search will find a solution. Alright, I'm on the edge of my seat to see what sort of amazingly low move counts these new depths will bring us. Well, that's disappointing. I think the lack of improvement is because needing deeper depths in the second phase is quite rare, while in the first phase, finding shorter solutions can often be counterproductive. Like, for example, say a 12-move first phase resulted in an 8-move second phase, so a 20-move solution put together. It's entirely possible that finding a faster 11-move first phase could put the cube in an awkward state that then requires 13 moves in the second phase for a worse solution overall. So if we're on the hunt for short solutions, we really need to try many different ways of completing the first phase and see how they all pan out. That is what this function is for. It doesn't follow the shortest path to the domino state, but rather recursively tries all paths that lead there in a specified number of moves. Then all these first phase solutions, barring duplicates of course, are gathered into a big list for us to test. So over here we're working our way up through progressively longer first phase solutions, and running the second phase on each of them to see if the overall result is better than whatever we've found so far. What's nice is that each time we find a shorter solution, that reduces the depth we need to bother searching in the second phase before we can reject it as being not good enough. So we don't actually need to fully solve the vast majority of second phases. Okay, let's see how this multi-search pans out. I'm going to look at just the time bars first, since I'm struggling to fit everything on the screen again. And understandably the time has shot up a fair bit, averaging around 3.5 seconds. But still, that's faster than what we started with, and it's now checking often thousands of solutions rather than just finding a single one, so that's pretty cool. At least it will be if it actually translates into shorter solutions, so let's bring on the move bars. Previously we were averaging 23.2 with a worst solve of 27, and now that is down to 19.9 moves on average, with the worst being a 22. I'm honestly thrilled to see the average dip down below 20, so just give me a second here to celebrate. Woo! Here are the move distributions we had with our very first version of the Domino solver today, and after all the improvements we've made, here's how it's looking now. But I've been so focused on all the metrics, we haven't seen it actually solving the cube in a while. So let's fix that. I'll scramble one up nice and thoroughly, and then let's sit back and watch it do its thing. I find it super satisfying how quickly it all comes together now. Of course, there is still room to improve. We know that most cubes are solvable in 18 moves, and all within 20. But I'm pretty happy with where we've got to today. I want to end off just for fun with one final suggestion of sorts, which was to try Raytracing the Rubik's Cube. So I'll fire up that old project, and there's a little test scene here with 2 convenient cubes that we can swap out for the Rubik's variety. Then I'll enable the renderer, and I think they look pretty good in there. The request was specifically to have it submerged in water for some reason, so there was this little fluid experiment we did. But it takes quite a while to render the whole thing, so I'm just going to load up a single frame from there, enable the ray tracer, and plop the cube in. I hope that counts for something. We could do a little animation in a simpler scene though, like if this monkey doesn't mind moving out for a moment, we can put the cube in here, and let's maybe make the walls a little reflective so we can see the other sides of the cube as well. Then I'll run the solver and leave it to render. Okay, that is all for today. I'll probably be taking a break from cubes for a while, but I nonetheless welcome any suggestions you might have, cube related or otherwise. Alright, until next time, thanks for watching.